Hi, welcome back to this video series on cryptography. Today I'm going to continue my discussion on quadratic residues in composite groups. The question is, how do we decide whether a given number is a quadratic residue or not in a composite group? For example, what if you have your group, say, let's take a simple composite group, 15, right? Z star 15 made of composite numbers 3 and 5, right? How do we know whether a given element here is a quadratic residue? Well, Z star 15 is such a small group, we could try whether we can find a square root, right? For example, we are given a number. We check each and every number in the Z star 15 group and to see whether the square of that number is equal to the number that we are looking for. Say I have been given a number X, right, which belongs to Z star 15. All I have to do is try all other numbers in the set until I get an equation like this, right? Y square equal to X. Okay? And then we know for sure that Y is a square root of X. Okay, in this case, N is 15. Okay, so but that won't work if our group is very large, right? If I have my N to be about the size of say 2048-bit number, that means how many elements are there? Roughly 2 power 2048 elements in the group. That's a lot of elements to try, and that won't work. Okay. However, there is a nice, interesting trick. Suppose you know the factors of n. Okay, n is made of 2 primes, right? P and Q, distinct odd primes. In that case, it's possible to check whether a number is a quadratic residue or not. Okay, all we have to do is take the number x, right? Project it to Z star P. How do we do that? All we have to do is take X mod P, right? That will give us the projection to Z star P, okay? And then do the same with mod Q, okay? And now we can check whether this element is a quadratic residue in Z star P, and this element is a quadratic residue in Z star Q, okay? Remember, X mod P belongs to Z star P because P is a prime, okay? And X mod P will be from 1 all the way to P minus 1, right? Of course, we assume X is non-zero, okay? That's because X is coming from Z star 15, okay? We can check whether X mod P is a quadratic residue, X mod Q is a quadratic residue. Okay, that's simple to do. How do we check that? We have learned earlier that an element X is a quadratic residue in Z star P or Z star Q if and only if this particular property is true, right? X power P minus 1 by 2 is congruent to 1 mod P. Sometimes I put 3 lines, sometimes I don't, but anyway, it's the same thing. It's congruent to 1 mod P. If this is true, then we know that X is a quadratic residue in Z star P. So we can use this test to decide whether a given number is quadratic residue or not. Of course, the caveat is that you need to know the factors of n. If you don't know the factors of n, you cannot apply this theorem because P, you don't know the P and you don't know the Q either. Okay, so this is an important thing we need to remember, and we need to make use of this fact for constructing a crypto system based on this notion of quadratic residue or non-quadratic residue. Okay, so what I have explained to you so far is that if we know the factors of n, namely P and Q, it is easy to decide and test whether a given number X is a quadratic residue or not. Okay, there is one more important fact, a very interesting fact actually. There is a concept called Jacobi symbol, which I will talk in the next segment, that can be used to test whether a number is a non-quadratic. Okay, it's not quadratic, we can check. There's something called Jacobi symbol. Okay, what it is basically saying is that you take your number X, what it is people write it like this way, X, N. Okay, how do we compute this? This symbol is computed using rules of number theory. Without knowing the factors of n, we can compute the Jacobi symbol, okay? That's the important fact. If the Jacobi symbol is -1, you know for sure your X is not a quadratic residue, okay? X cannot be an element in the quadratic residue. It's not possible. The question now is, how do we compute this Jacobi symbol? That I will talk in the next segment. There is interesting property of Jacobi symbol is that Jacobi symbol of X is actually equal to product of the Legendre symbol. Okay, what is the Legendre symbol? Is basically, I will explain it to you in a moment. This is called Legendre symbol. Okay, if there are two factors, this is basically the Jacobi symbol. So now let me explain this part. This is P and Q primes, right? So we call this Legendre symbol. So Legendre symbol is very nice idea. Suppose you have a prime P. How do we compute the Legendre symbol of this? This is basically not given by this notation, and it has this interesting definition. This is equal to 1 if X is a quadratic residue. Otherwise, is equal to a couple of possibilities we need to enumerate. Is equal to -1 if X is not a quadratic residue. Okay, and there's a third possibility is that is equal to 0 if X is 0 or multiples of P. Okay, so these are the three possibilities for the Legendre symbol. And there is one more interesting property that connects the Legendre symbol and Euler's criterion that I talked about in the previous segment. Very briefly, I also touched upon it earlier, is that the Legendre symbol can also be computed using this nice property that connects Euler and Legendre's criterion. What it means is that in order to compute the Legendre symbol, it's enough to just do x power p minus 1 by 2. And if this value is 1, then we know for sure the x is a quadratic residue. Otherwise, x is not a quadratic residue. So we can use this fact now and compute the Jacobi symbol, because the Jacobi symbol, if you know the factors, you can directly apply. Okay, this model. If you don't know the factors, there is a nice way to compute j of x without knowing the prime factors of n. It's possible. And again, if you know it is -1, you can be sure that your number x cannot be quadratic residue in z star n, right? But what happens if Jacobi symbol is 1? Okay, if Jacobi symbol is 1, we cannot conclude anything. The reason is that it could be possible that the Legendre symbol here that you're seeing, this is 1 and this is 1. 1 into 1 is 1. Or it can also be -1 here and -1 here. Therefore, we cannot conclude whether x is a quadratic residue or not. Just knowing Jacobi symbol of x is 1 doesn't imply that x is a quadratic residue. Okay, so this is the fundamental concept used in the Goldwasser-Mikli crypto system that I will talk in one of the future segments. But this is an important concept. So keep in mind that Jacobi symbol of x being 1 doesn't tell you anything whether x is a quadratic residue or not. But we do know for sure if Jacobi symbol is -1, x cannot be quadratic residue. Okay, without even knowing the factors of n, we can compute the Jacobi symbol, which we will talk in the next segment. Okay, that's basically it. And it's very easy now to connect the Legendre symbol and the Jacobi symbol. Once you have this formalism in place, you can see how these things are connected to each other. Okay, thank you very much. That's all.